Um, my current role is a lecturer. I work at CPUT. I'm working in the maritime department. Well, I'm from the mechanical. I studied mechanical, did the diploma, did the BTech, specialized my master's in energy. I've been in, and fortunate for you, the mechanical testing industry for was it how many years? 4.5 years, and that's when I got into lecturing. So you kind of you fortunately got a guy who's well experienced to do to you these things that he's talking about, the things that he's seen. I can relate a lot of good experience for you. And yeah, and I'm obviously teaching. I've taught a lot of subjects in the last 5 years, ranging from strength of materials to mechanics of machines, thermodynamics, electrotech, all on the mechanical side, obviously. I've done mathematics, I've done physics. I'm also doing computers this year. I mentioned thermodynamics. I've done quite a few subjects at both, basically NQ of level 5 and 6 for us. That's S3 and S4. All right. So yeah, so that's gonna be me. Um, there's a lot of other experience I can mention, but that's the main stuff. I was also applying for my professional registration, my PR Tech Eng. That'll be in January. So hopefully by next year, I'll get that PR Tech Eng badge, so to say. So that's me, right? So I've been in academia for a while. Um, through my masters, yeah, it's a lot of my elements of research is within solar thermal heat pumps. That's my area of specialization. So anything solar, we can possibly talk both solar thermal, and solar PV. All right. So I think what I want to just quickly do, just to make this worthwhile, especially when I'm hearing Louis is not familiar with these principles, right? I just want to give a brief, very brief presentation. And by the way, this is from my lectures, which I've done. So it's gonna be worth your while to just to quickly, just like for 5 minutes, 10 minutes, I'm just gonna talk through it, and then eventually we're just gonna begin solving problems. So yeah, I don't wanna. So James, can you see the slides? I believe it's all James over here.
Yeah.
Okay, cool. Right. So yeah. Cool. So again, right, just to give you an overview of what the subject is about, right? And I mean, guys from mechanical obviously know this, but just for the guys who are not mechanical, right? So it's strength of materials. Um, the purpose of strength of materials is one main thing, right? Any mechanical structure we build, right? We want to ensure it's gonna last. This subject is exactly the same for civil engineers, but instead of them talking about bridges, staircases, buildings, we are talking about mechanical structure. So we are looking at all the forces present, right, within mechanical structures, and we are ensuring that those certain structures don't fail. So, like, what you're seeing here is obviously a bolt failing. It's a very common thing, but the bolt is failing in two different ways over there. One is completely right through, and one has this kind of face of here, right? That failures, right, tells us what kind of failure it was like, and then obviously tell us through the loading condition. Like here we have a brittle failure and a ductile failure, things like that. Okay. This was a shaft which was grossly overloaded by torsional stress, right? So that's like a twisting motion, right? And just completely snaps off. So, and by the way, that's a mechanical element, which is essentially a shaft, right? So again, we want to make sure whatever mechanical structure we have is going to last for some time. That's the purpose of this, right? Again, I just want to give you some examples of mechanical structures. This is from Wikipedia. There's boilers and pressure vessels, there's coaches and carriages, cranes, elevators, escalators, marine vessels, and hulls. I mean, the actual ship. There's a lot more mechanical structures. So I'm just letting you know the mindset you must have when you're doing these things is that, okay, it's all about having a structure. I'm looking for a particular image now. I'll show you now what I mean by mechanical structure. There's a lot of stuff I have here. Let me show you here. Okay, yeah, where is this? Yeah, like this. This is a maritime thing. Where is this allowing? Someone allow the person in now? Yeah, I can't even see. Okay, cool. So, like, where's my slide now? just took 3 minutes off now. I don't know if you guys can you guys see this propeller with a shaft, engine, flywheel, clutch, gearbox? Can you guys see it?
Yes, we can see it.
Yes.
Yeah. So this is an example of mechanical structure, right? You might not know it now, but like the shaft itself, the loads present in the shaft. Excuse me, guys. Is this person? I don't know, where is this person? Don't want to get in the meeting, but now I can't even see where they are. Oh, there we go. Okay. I'm allowing them. Yeah, there we go. Okay. Cool. Good afternoon, students. We are just doing some background here before I actually embark on this. So this is an example of a mechanical structure. And a shaft, the loads on a shaft, right? And when we design shafts, it's a torque load and a bending load. I mean, essentially, we think about it, the shaft is actually a beam. So there's a whole analysis what you actually conduct. And I mean by analysis, design, and calculations, what you actually must go through in order to determine which is appropriate size of the shaft which must be used. I don't know if I'm giving a good background of what's happening here. Gents, are you all on the same page?
Yes, sir.
Okay, cool, man. Thanks.
Yes.
Louis, electrical?
Yes, I'm still on the same page.
Okay, cool. So that's just basically it. I don't want to go too deep into what I'm looking at, but again, I just want to go to this. Where's this images? So what are you looking at here, right? And this is the basic definition of strength of materials. Then I want to just go through these loads. So they're saying there, the strength of materials is the study of engineering materials and the mechanical behavior in general, such as stress, deformation, strain, and stress and strain relationships, right? And it's all about looking at an element under the influence of an externally applied load. So we have an element being a shaft maybe, right? Or some kind of structure. We apply loads to it, and then we can see how it behaves, right? And obviously, when we're seeing how it behaves, we don't want that structure to fail. Like, what are its limits? Okay, so I think in the first chapter, which is quite similar to what I've done, is that you must be aware these are the fundamental mechanical loads you're seeing right in front of you. So the first one is tension. I think we're all familiar with that. A pulling force, compression, shearing, torsion, and bending. Those are the 5 fundamental mechanical loads. And what I mean by that, any mechanical structure is subjected to either one of them, 2 of them, 3 of them, or all of them at the same time. Am I clear, everyone?
Yes.
Yes. So that's the mindset you want to be using on here. So when we do the analysis of a structure, you look at a particular structure, and determine, okay, what loads are present on the structure, and then based on those loads, they all have their own set of equations, and therefore we'll be able to determine the size of the object element we must design, or we're going to predict when that thing will fail. So this is what the whole course is essentially about, but in different individual components. So yeah, I just think I wanted to start with that. Okay. But let's move on back to the calculation stuff. Guys, are there any questions? Am I going? Is it too over your head or what? I'm hoping everyone read at least.
Are we still following?
Okay, cool.
I'm still
So what I'm
following.
gonna do now, I'm gonna move on to actually just solving problems, right? I'm gonna do a small warm up just to give you a feel of how I conduct the tutoring lessons, and then I'd like us to work through the problems I've sent you, right? But please, guys, engage as much as possible. I really want you guys to be successful for your whatever individual goals which we have. So let me quickly just share the whiteboard, and then let's begin. Here's this whiteboard. Okay, just give me a second. This is not what I'm looking for. Window. Okay, here we go. Right, so this is on the assumption that you guys have an idea of what the chapter is about, right? So this is where we are. Okay, I'm gonna leave it to the house and ask anyone, right? What's the formula for stress? Does everyone know the formula for stress?
Yes, sir.
Give it to me, man.
Area.
Give it to me, please.
It's force over area.
It's force over area. So sigma is force over area, right? Okay. Is everyone aware of this? Let me just I'll check everyone's names. Where are we? Okay, Wusi, yeah, everyone, nice. Angus, Anga, Sumila, right? That's the formula for stress, right? And again, students, when you look at this, right? Always when you look at a formula, right? Always imagine a formula to be the relationship between variables, right? I'll say it again. A formula is a relationship, right? Equals relationship between variables, right? Very important. It's just not the formula, right? Relationship between variables. What do I mean by this, right? And I'm just giving you I'm being very lectury here now, but I'm just giving you that mindset, which is very necessary. I mean, we're all engineers here, but so what I mean by this is that if you increase the force, right, what happens to the stress, right? Can anyone tell me?
If you increase the force,
Yes, what happens to the stress?
I think the stress increases as well.
Exactly, right? So can you already see that relationship, right? That's very important. So if you have a structure, right, and it's designed for a certain load, and you keep applying more force, it will exceed that particular stress limit and the thing will break. So again, increase the force, the stress will increase, right? Okay,
Yes.
right. Let's do this now. What happens now if I decrease the area? What happens to the stress?
If you decrease the area,
Yes,
what happens to the stress?
100%.
It still increases.
Yes, it still increases, exactly, right? That's very important. And then obviously converse to that, if you increase the area, the stress decreases, right?
Yes.
So again, think of a formula as a relationship between variables. Guys, I mean, we're all engineers. I always recommend all my students that that's the way you must view this. I don't think it's just numbers. It's not numbers. It's telling you this one is playing with that one. This one is playing with that one. And sometimes this one affects 3 variables. Sometimes it affects 2. Sometimes it affects 1. This basic formula, you know, I'll just tell you, if we design something, right, let's say it's like this diameter, right? So whatever diameter it is. And there's a particular load on here, right? And whatever load this is, it somehow breaks this thing. Do you know what's the first thing we do as engineers? We just get a bigger size. Is it not so?
Again?
So I'll say that again. So imagine we have some element, right? We put on a load, and this load breaks this particular thing, right?
Yeah.
So now we need to replace it, right? So all we do to replace it, what we typically do, we just get a bigger one. You know what I'm saying to you? Instead of 20 more, maybe we get 30 more. You understand? So my point here, what I'm trying to make is that we increase the area, therefore the stress reduces, therefore the structure will stay fine. I don't know if we're all on the same page there. We all get that? Yes or no? Louis got it. He says he got it. Anga? Yeah. So I'm just trying to show you, man, very briefly, like what this actually, yeah, what this, you know, obviously I'm accelerating the knowledge here, but this is the idea of that formula. But anyway, guys, let's quickly solve these things, man. Okay. So we've got stress equals force over area, right? So let's read the question. We're going to be basically solving. So it says, calculate to the nearest millimeter the diameter of a steel rod that must carry a tensile load of 100 kilonewtons without the stress being more than 90 megapascals, right? I'm assuming we all know how to define our variables, or declare them. So F in this case will be 100 kilonewtons. And the stress is going to be 90 megapascal, right? I'm sure we all know SI units. It's a simple thing. We plug those values in over here. 90 MPa
times 6.
Yeah, times 6. Exactly. That's megapascals. And then we divide that by the area, 100%. Let me just allow this person in, then I'll get back here. Cool. Okay, cool. So can we all solve for the area? Guys, I will not be talking. We are working today. We didn't come here to play. Let's compute that area. Does anyone need a crash course on a calculator? How a calculator works?
Pi, this is what is it? Pi d squared over 4.
Yeah. So let's first find the area of Wusi, then we're going to do the pi squared the pi squared d4. Just get the area itself in meters squared, and then we'll get back to that one. Yeah. Okay, Louis, you want to solve it, Angus? Angus, Anga, can you guys hear me?
Yes, sir. Can you hear you?
100%, man. Great. Okay.
It's 1.1 times 10 to the power -3.
There we go. 1.1 times 10 to the power -3 meters cubed. Hi. Hey, someone's talking there. Oh. Okay, cool. Is there no other decimals besides that? It feels very unengineering to see that 2 decimals. I feel like I'm in high school there. Louis, give us some numbers there, man.
Yeah, it's comma 11111 till whenever else. So
Oh, okay.
just round it off to when
-3.
necessary.
Okay, nice. -3, right? Fine. Meters squared, right? Okay, so what's important of this particular section? You must obviously know your areas. That is standard over there. So because we're dealing with a steel rod, I'm sure you guys don't know what a rod is. I should rather say shaft, look something like that. Just forgive my skew drawing, right? I have to mention this, and I'll mention it now. The cross section here, right, is a circle. So obviously the high school way is pi r squared, right? But the big man way is, or the big man or woman, it's pi d squared. This is the same thing. The reason why we particularly use this one is when you buy shafts, we don't say to a supplier, give me a shaft radius of, you know what I mean, 10 millimeters. We talk diameter. So we prefer to use that one over there. So then what we do now, the area for that, so it's going to be pi over 4 d squared equals 1.1 times that. And obviously we should solve for d squared. I believe you all can do that. I'll just set it up for you guys here. -3 times pi, no, times 4 divided by pi. Times 4 divided by pi. And obviously we must root this guy, right? Okay. Woolsey, Angus, guys, what is my diameter there?
I don't have a calculator on me as I'm in my car driving and sitting in the class at the same time.
Okay, cool. No stress, man. No stress.
It's 37.612 times 10 to the power -3.
Okay, 37 point.
Mm.
Let me just check here. 1 point. Can we all agree on that answer? I'm not even sure. I'm working it out now. Yeah, so it's 0. That's in meters. It's 0.0. Just give me a second. 0.037. So you get 6, right? I get 4 for somebody. Okay, yeah. Say 4.2.
Yeah, it's
376. Yeah, okay, it's fine. I get 0.03742. I'm using the exact value, and I didn't add the other decimal places. I don't even we save those values.
Yeah, I used what I got area, the 1,111.
Yeah, so Louis more accurate. But okay, that's fine. So we'll just call it 37, around 37, and obviously this is in meters. Therefore, we're talking 37.42 millimeters. Okay? Okay. Is that clear to everyone? Are we happy with this? Students?
I'm following you. I'm fine.
Okay,
Don't
you
know
happy?
about the people.
Okay. Mia, Angus, Anga, Mangaliso, Wusi.
I'm happy.
100%.
Answer.
Okay. Okay, so just before we move on, right? How did you find this solving the questions like this? Is this useful? Is this what you expected, or I'm just curious to know.
Yeah, it's useful stuff.
Great.
I think if anybody has a problem, it will pop up as we solve the question. So I think this method it would work.
Okay, I'm happy. So this is what we're basically going to be doing, right? Tackling problems, and then yeah. I do want to make you aware, and this is obviously just me being a lecturer again. The area we always talk about, right? And I'm going to paste this image for you here before we proceed to those questions which I've given to you. Okay. You must always remember, right? When we are computing for stress, right? It must be the area. Just give me a second. We always use the area perpendicular to the force. I hope that's clear to everyone, right? So if the force is here, it must be that area over there. It confuses a lot of students. So it must always be like on this face over here. I'll show you now. So you see what the force. Yes, go for it.
So with the first question you shared with us in the homework, I first used the wrong area and then afterwards okay.
Yes, you see what I mean? You see what I mean? That's why I'm mentioning it. It must be that area. A lot of people get confused. And this is only, right, Louis, for when it's a tensile and a compressive load. You see what I'm saying to you?
I'll make a note.
Yeah, so that's why I'm deliberately bringing it up. Because a lot of people think, so when you're dealing with shear, for instance, the area is completely different now. You see? So that is why I'm just throwing it out for everyone.
So I've got a question. What will the area be in a cylinder? For example, a tube but not a solid center. It's like a tube.
I know, brother. Got you. So if we have a tube like that, right? You know, I hope you can. When you go draw a thing. Okay, got that right? Like this. That's hollow. You mean, right?
Yeah, hollow in the center.
Yeah, and then let's say we're putting a load exactly in the middle, right? We must be careful the scenario, but there's a theoretical thing. What you basically do, the area of this is going to be pi over 4 big D, which is obviously the diameter of the outside, minus the diameter of the inside. You got me?
Okay, so that will be the mean diameter of the cylinder.
That's what I mean, the mean. It's the actual area. Remember, we're talking about area here. So not mean.
Yeah.
So we're taking this area over here, this over here, this over here. You see here?
Yeah.
So it's the big D minus the small one in the middle. That's what we're looking at. Assuming the load is applied exactly where I'm showing to you. Am I clear?
Yeah.
Okay, 100% chance. Okay. So students, let's solve. Let's move on to the tutorial, right? I think that's now just a warm up to see where we are, and we're gonna pursue on that tutorial. Okay, so let me just put that question up for you, and then we can begin. Okay, I don't know if everyone has solved this. Do you want me to give you an opportunity to try and solve it at least? Or so this is the question. Okay. So again, I think the finger number is wrong. So what's happening here, guys? We have this bar with a hole in the middle. I'm not sure exactly where we might see this in a real life basis. And what we're basically doing is applying a 15 kilonewton load. And what they want from this is the stress induced within this particular thing. Okay. So again, it's a basic problem. And that's going to be stress equals force over area, right? So I'd like to go to the house. Guys, tell me which area do we use here? Can someone tell me? I'm just going to put this here.
I can tell you, as I made a mistake of using the wrong one, but it's the 25 millimeter and the 12 millimeter.
Yes.
It's not the 25 and the 70, but the 25 and the 12. You work out that area of that side.
Yes, that's correct. So if I'm going to do a side view of this one, right? So the bar looks like this, assuming the force is coming exactly in the middle. What you can also see here, right? We have this circle, actually this over here. You agree with me, right? So the force is coming exactly in this middle. Do you see this over here? So this is now the whole, guys, right? I'm sure we know drawings, right? And the area we're using is this area, colleagues. This one over here. You see here? That one. But we must bear in mind, we've got a hole in the middle. You see there? So the area for this one is going to be 12, right? And 25. However, we've lost some length in the middle. So it's going to be, so this is 25. And that's going to be 12. So the actual area, Louis, I hope you agree with me here, is the area in this case is going to be 25. It's going to be minus this. Remember, we have to minus this portion in the middle here, right? You guys agree with me? Minus the 15. Then times by the 12. Obviously, this is going to be in millimeters. Are we all on the same page here? I'll write it better. 0.025 minus 0.015 times 0.012. Are we all on the same page?
I did it a bit different. I worked out of the rectangular, the area, and then of the whole, and then I just subtract the one from the.
That's fine.
From the other.
The answer for this, let me just check this answer. So it should be like this. I don't know what answer you got. The answer for this was, let me just quickly check. It should be 125 megapascals. That's the actual answer.
Yeah, I see. I got 121.6. So I don't. It's a bit out.
Out, yeah. It should be
120. I got 121.67 megapascals. So.
Oh, I see. Nah, so it should be this. So what I'm saying is that this is a cross-sectional area, but we have to subtract this portion here because this is not here. You know what I'm saying to you? The load is coming through here. The area in question is actually this load, this area over here.
Mm-hmm.
Yeah. Other colleagues, Busi, Anga, Angus.
I'm quite lost, eh?
Oh, okay, good. Mangaliso, Tomila. So guys, I'll come back here again, right? I'm trying to get you on the same page. So remember, we have to use this area here. I don't know if you all can see that. This area over here. Yeah. But remember that there's a hole here. You see there?
Yes.
So what I'm saying is if you look here, I'm drawing an eye. We'll see, right? Ah, man. This is the view you see, right? You see?
Yeah.
So what I've done here is shown you that there's a hole over here. This portion here. So what I'm saying is that when you're applying a load through the center, like imagine the force coming out of the page, this green dot, it's being pulled out. The area you need is to look at this area over here. So you must say 25 minus that hole, right? Remember, this is diameter. So it's from here to here, it's diameter of 15. You see that?
Yeah.
So saying it's 25 minus 15, which will give you that side, and then this over here will be 12. It's kind of a trick question, this one. What are you not understanding? What are you not seeing?
Where is the 10 to the power negative 3 coming from then?
Oh, so this is just a notation. And remember, 10 to the power negative 3 is it's a shortcut for millimeter, man. It's basically dividing by 1000, man. Remember, this is like.
So we calculate stress in meters, not in millimeters.
Yes. Meters is the base unit here. So I was just showing you this part here for the sake of the minusing, yeah.
That's 2 meters, because I understand the area of
okay.
Thing, which is
that, so anyway,
some spread, né? But now you're minusing the 15 meter because we have a hole inside.
100%.
I was just confused by that 10 to the power negative 3. Where is it coming from?
Okay, so again, this is 1 times 10 to the power negative 3. If you remember your exponents, right, you can bring this down like this. And what's 10 to the power 3? It's 1000. So I'm basically dividing by 1000.
I understand that part. It's just that I was confused if we're working on meters or millimeters. So you're saying we're working on meters?
Always meters. That's a base unit, most 100%. Okay. Thanks.
Okay, no, I understand now.
Yeah. Okay. See, I'm treating like you guys know things, man. That is why I'm a bit cautious. Okay, so the area here you should get is 120 times 10 to the power negative 6 meters squared. Okay, that's the area there. Again, as engineers, we work in powers of 3, 6, and 9. I think we're all aware of that. 3, 6, 9, 12, etc., etc. you're not sure to get 6, I can show you on the calculator.
Sorry, sir.
Yes, dear.
I just calculated using both methods, which is the 25 minus 15 times 12, and also calculated both areas, the one for 25 times 12 and the one using the diameter of the hole, and I am getting the same answer.
Oh, interesting. Okay,
So,
fantastic.
that guy that used that formula, I'm getting the same answer. Maybe there's a mistake that he made.
Okay, cool. That's fantastic. You must share with us in the group. I appreciate that. That is Jadanga. Okay, cool. So again, right? So once we have this, it's a sum of stress equals force over area problem now. So our load is 15 kilonewtons. Right? And then obviously we have divide by 120 times 10 to the power negative 6. Okay. And I think we all can do that. Let's quickly check. And we should get 125 megapascals. All right. And we should actually put, if we really want to be fancy, a T there to tell us the sense of the thing, which is a tensile. Is there any questions, guys, with this one? Angus, Sumila, Anga, Mangaliso, Louis, Vusi.
Question.
No.
Okay. Okay.
No,
cool.
no questions.
Yes.
Calculations is right to me. Yeah.
Okay, thanks.
They're just following the formula.
Okay, cool. Right. So that is the first question I prepared there. We can do the next one, right? I hope you all yeah, okay. Let's try the next one. Again, this is a different the next question is a different concept at play here. So I hope you're aware of these concepts. Okay. So I'm gonna paste it here. Like this. And there we go. I just wanna put up the main formulas for this, the concepts, which is stress over area. I mean force over area, which is stress. They do mention something about change in length. There is a concept called strain, and the strain is essentially the change in length over length, right? So, and the last one is going to be something called your elastic modulus, right? Which is going to be stress over strain. Is anyone familiar with this concept? Did anyone go through the stuff?
Yes, sir.
Oh, okay, cool. They call this X sometimes in your books. I don't wanna. I'm not sure if you guys are familiar. So, Okay, so in this case, right, he's back to I think what Angus he was asking. So we have a hollow steel tube, right? So it looks like this, some tube, a pipe, if you will, maybe. Goes like that. They actually use different formulas for pipes, but anyway, it's thin cylinder formulas. Okay, so then what they're telling you here is there's a load on this pipe, right, of 75 kilonewtons, right? We're not sure what this load could possibly be. Maybe someone can tell us. It's applying this tensile load, I believe, right? It's not being compressed, so therefore the length is increasing. And they're telling you that the maximum stress of the pipe is 90. What I find interesting about this, and I want to tell you guys, is that when they always give you the stress of a particular object, right, they typically each material will have its own stresses, man. So like we have 316 Australian steel, it has a yield stress of around 240 and a UTS of around 250. So your stress is actually a given. What we're always actually working for is sizes. So in this case, like we're working for the diameters of the tube. There's a classical design thing in mechanical where you know the loading condition and you know the type of material you're going to use, right? And you need to determine what size of tube you must use to install what everything. I hope I'm clear with everyone, just the thinking of what's happening with this question. So anyway, They're saying we have a diameter ratio of 0.8 to 1, right? So are they saying is it big D over small d? I'm not sure. Is it was a small d over big D? Right? The ratio is 0.8 to 1. I believe it's like this. Am I correct? You think it's like do you think it's like that?
Yes, it's like that.
Correct, sir.
Okay, cool. I'm just making sure, you know, sometimes you can easily slip on such things. Okay, so then obviously we need to compute now. This is going to be very algebraic type problem. We need to compute this thing over here. Let's see. So now, first thing we're going to do is get small d in terms of big D. I hope we're doing the right thing here. You never know these numbers, right? And so then we want to be plugging in and solving this thing. Okay, let me quickly see. So we know our base formula. It's going to be stress or force over area. We are given stress, which is 90 megapascals. That's stress within the tube. We've got a force of 75 kilonewtons, and therefore we must compute the area now, right? So what is the area? Okay. I'm going to work it out. You can just tell me, I'll work it out. You can just tell me if you agree with me. You should get 8.333 times 10 to the power negative 4. Can I go negative 6? Yeah, let me go negative 6 about that. So 833,33 times 10 to the negative 6 meters squared. Okay. I'm all happy with that answer?
Yes, sir.
Yes, sir.
Louis, Angus, I think Angus
Yes,
said
sir.
yes.
Yes,
We'll
yes,
see.
sir.
Sure.
Yeah.
Right. So then we know the area. So the area, again, is a tube, right? So it's going to be pi over 4, right? Big D squared minus small d squared, right? Equals 833.33 times 10 to the power 6, right? I'll do the next step for you and you can solve for me. So we have small d in terms of big D. So let's quickly do that. So it's a pi over 4, which we can easily sort out. So we're going to keep big D, but we know that small d is 0.8 big D, right? But remember, we must close that guy off and we must square him. Hope I'm clear to everyone. Let me put square brackets here. We can just differentiate the brackets. So that's big D squared big D squared minus 0.8 big D squared, right? Close that bracket off, equals 833.33 times 10 to the power 6. All right, are we happy with that? So you guys have to solve that now. Algebra. You guys concur with that over there? Usi, Louis, Anga.
Yes, sir.
100%. Okay, so just try to solve for D there. Yeah.
I got 0.0543.
Is that for D?
Yes, that's correct. Yes.
0.543, right?
No, 0.0543.
Okay, D 0.0543. I believe that's correct, eh? Yeah. That's correct. Electrical engineers hard at work. Good to see. And obviously small d, we just multiply that by 0.8. Yep. 0.8. Okay. Colleagues, are we on the same page? Are we all on the same page? So that's 4. It's 4. 4. I'm at 4. And small d will be that. So that's the size of our tube over here.
Obviously, we'll just have to make it millimeters as the question
Exactly.
asked. Yeah,
Yeah.
so.
Yeah, I was going to say that afterwards. Yeah. I mean, you want to leave it in like the standard form of millimeters. That's correct. Yeah. Is everyone understanding this concept? Is there no problems? You know, we're all winning together. Got that? Yeah. Any questions? Who's making sounds there? Lucy.
No,
Lucy, you
can't-
winning?
Yes, man.
Yeah. Are you winning here?
Yeah.
Okay, great. Guys, any questions? Can we move on? Is there anything uncertain? Or just too much for you? Okay. Great. So the next question is, calculate the tube's change in length, right? So this, and I give you the elastic modulus of 130. Again, there is a material property. So different materials will have different elastic modulus, right? So steel has around 200. I believe this could be copper is around 100, 130 depending, right? Again, it's a material property that's kind of given to you. It's known published data already. So now we need to find the change in length. Now I just want to show you something quite useful. I'm using this formula over here. We have the elastic modulus, right, equals stress over strain. We put it into its individual forms. I just want to show you something. Okay, now I want to keep the stress, right? I want to keep the stress. And then your strain is your change in length, which I believe they call X in the Northlink textbooks over here, the N5 textbooks divided by L. Then if you do a nice flip in times of this, all right? Just give me a second. A nice flip in times of this. You get stress L over X, right? And then you flip this, you sort the elastic modulus and that out. E, and you have stress LE. So this is a nice short formula, stress LE, which will give you the change in length immediately. Are you guys familiar with that one? This is a quick manipulation of that formula to make your life easy. It becomes useful when you do compound bars anyway. Is anyone familiar with that? Sumila, Anga, Angus, Louis.
Yes,
Okay.
No, I'm not familiar with that, but seeing it as I go on. Yeah.
Okay, quite great, fantastic.
Following.
Right. So again, this is important. You'll see in compound bars. This becomes very prevalent, which is part of the same chapter. So I'm just showing you right now that know this one, right? So anyway, they're asking for the tube change in length, and they give you that there. So using that formula, this is going to be A. Just put B over here. We know that it's X stress L over E. Stress is 90 megapascals. The length was given, I believe. It's a 2-meter long pipe. And then you divide that guy by 130 gigapascals times 10 to the 9. What this value is telling us is that under this given load, how long this pipe actually extended by, and typically is very small. So can we get that value from the other colleagues?
Okay, I'm getting 1.385 millimeters.
1.385 millimeters. Okay, thank you, Anga. Thank you very much. So it should be 1.385 millimeters, right? So obviously that obviously be 0.00. So you can see it actually extended by just over a mil. You can obviously check that out. Okay. Any questions, guys? Is this straightforward? Are we on the same page? This is also 1.3846. Just writing it like this is all meters. Yeah. Colleagues, are we all on the same page? Anga, Angus, Louis, Magaliso, Sumila, Vusi. Are we here, guys? Are we present?
We are.
You said
Okay.
90
Yes,
to the
yes, sir.
power 3, but it's 90 to the power 6 times 2 for stress.
Oh yes, thank you very much. Thank you. Thank you. Yes, I made a mistake there. Okay, guys, cool. Should be 3, yes. Thank you very much. I slipped. I must that there. Okay, this should be 6, yes. Okay. Do you want to take a 5-minute breather? And then you want to get back, or you want to continue?
Let's continue.
100%. Okay. Cool.
If
Vusi was saying something. Okay.
if
Right.
that is 6, then I think the answer will change.
Yes, I changed the 3. It's 3 at the bottom. It's -3 in that case. It's just most you're just subtracting those variables. Remember exponents 6, 9.
-3, not -6 now.
Yes, I made it -3 now. I've done that. Don't even seen it here. Yeah. Okay, cool. Let's do the next one, all right? Again, guys, I'll talk to it now. I'll just move this to the side. Okay, maybe we will after the session we will talk about it. Let me park it for them. Okay. All right. Okay. Has anyone done this one as well? This question?
No, sir. Just
No,
Okay.
sir.
I also didn't attempt this one.
Okay, great. That's fine. All I want to say is that, like, I realize, like, like a trimester worth of work. I mean, I teach this kind of stuff in a semester. I mean, we all studied, So I don't know how people actually manage to do all of this stuff with proper detail and understanding in how many weeks is this? 2 months?
Yes,
sorry?
8 weeks. 8 weeks.
8 weeks. That's ridiculous, man. I don't know. I don't want to say anything around that. So okay. So I'm trying my best to articulate this, right? So this was my bread and butter for 4 years, so it's hopefully I can extend that knowledge nicely. So I'm just going to quickly go back, do a quick share some slides, and with this, I mean, I could talk like straight 2 hours on this test alone, what you're seeing in front of you. Okay. Can you guys see the slides over here?
yes.
Okay, great. Okay, cool. So I don't know, has anyone ever seen a tensile test like have you seen a tensile test being conducted ever? Who's familiar with a tensile test?
Not
Angus?
necessarily a tensile test, but in the marine industry, they normally do a loading test on a crane.
Nice.
So they fill a bag full of water.
Yes.
And then they will see the load capacity, what is the safe working load, and
nice.
it exceeds the safe working load.
Okay, great. Okay,
Yeah.
cool.
Also at Quebec as well, they do it frequently to test the overhead cranes.
Yeah.
Yeah.
Okay, cool. So I'm gonna give you a quick rundown of what happens here. Hope you guys can follow, right? And I'll give you some practical experience of how it's actually being done. So what do we have, right? Let me give you the story first, man. Let me just go to the story, man, and then I'll come back to the stuff here. It's a lot of examples. So this is a typical story of how it works, right? Someone joining you. So this is when I was working at this company called Gascon. They were building pressure vessels, and both marine and there's more. How it typically works. So before you build any structure, right? You typically order a plate from a supplier, right? Now, depending on the supplier, the supplier is good, right? They'll issue the issue with a 3.2 certificate. That 3.2 certificate is basically telling you that the mold where they manufactured the plate has been tested, tested the material, and then an inspector and a third-party inspector has witnessed a retest of that. So what I would typically get is 3.1 certificates, and we had to retest the material to ensure that the material is, it's exactly what they say it is. So a material will come in, right? We'll get a material certificate. On the material certificate, it was from China. That we can't really trust Chinese, and I shouldn't be saying that, but they'll give you values, man. They'll actually give you the UTS. It's all in this. They give you the chemical composition. Let me just make it big for you. Time to make this video educational. Oh, there we go. What happened now? Yeah, can you see there? That's an actual material test certificate, right? So here to tell you the heat number, the cost number of the particular plate. It tells you the dimension of the plate, the weight of the plate. They done a chemical composition of the plate. And then can you see all this YS and TS and EL? Can you guys see those things?
Sorry, sir, the chart's not showing. I'm not sure if it's just me.
Okay, no, cool. Let me just have a look again. That's a material cert. Yeah, it's over here. Can you see it now?
Yes, I can see it.
100%. Thanks, man. So again, heat number would be the cost number. Tells you the size of the plate, weight of the plate, and this is the chemical composition of the plate, right? The elements in it. And then can you see this part over here, this part over here, this here, mechanical properties. You'll see there, yield stress, tensile stress, and elongation, right? This HRB is the hardness test. Can you guys see that over there? So these are actual, so what they do, the mold actually test the plate, and they'll give these properties. Based on these values, right, they can declare it's a particular standard. So basically all plates have, a standard. I don't know if I'm making sense. Like stainless steel have its own one. High carbon steel, medium carbon steel, low carbon steel have its own one. So I hope you all get that in terms of this thing. So this is what actually happens, right? So what I used to do rather, was actually, I get the plate, I machine a test sample, which is like that on the bottom. You see over there? I actually test the stuff. And then we check if it conforms to a particular standard. So we basically can see that the plate is, it can be used for construction or manufacturing. Am I clear to everyone just how the story works behind that?
Mm-hmm.
Okay, I don't know if I'm clear, guys, but anyway, it's fine. So the objective is we're talking about a tensile test here, right? Which is a very common test. There is a lab in Cape Town which does it as well. Again, I want to make you aware that there are actual grades or standards for each type of plate, right? These are grades for actually hull material, right? So if I get a plate from a supplier and they want to build on a hull, we're going to retest the stuff to make sure it conforms to the standards. I think we're all familiar with, standards and so on. So this is actually like one, one standard. Okay, so what happens in the actual tensile test? Real life story here. Let me go back. In a tensile test, I can't believe I'm lecturing this, is that you have a specimen, we put it in this machine over here, right? And you guys can see this. The machines look different, but they all kind of serve the same purpose. So we put a specimen in over here, which is where this red is. The bottom jaw will be stationary. It depends on the machine. The top jaw can also be stationary. And then this head over here moves up and basically pulls that specimen I showed you over here. Like this. You see over here? You see this one over here? Something like that. Am I clear to everyone? So it pulls like that. Can you see? Anga, can you see that? Louis?
Yes, sir.
Yeah, so that's exactly what happens, right? So we clip, we on the left hand side is the head where it's stationary, and then the other side is basically how we pull it, and it does exactly like that. And the next, eventually it breaks, right? So as we're pulling it, the machine, the tensile test machine, actually logs a graph of load and extension, or extension versus load. So if you have a mild steel specimen, what happens is it goes up, right? It dips for a bit, it goes like that, it gets the maximum load, and eventually breaks there. So that graph is a typical low carbon steel graph over there, right? And what do these things mean? Okay, so they give you some points A, B, C, D, E, and F, right? You see this region over here, this region over here, this A, region A, this over here, AB. Can you guys see that? Just over here.
Yes.
Yeah. That region is where you can apply any load, right? And then as long as you don't exceed that load, right? Let's say in this case B, the specimen will return to its original form. It's behaving basically like elastic. If you keep on applying it past this point here, the C, its yield point, it will not go back to its original state. So once you pass C, it permanently starts permanently deforming. Am I clear to everyone? Real life stuff.
Yes.
Louis?
Yes.
Yeah, so that's okay. So, and if you keep on loading the thing, it will come to this region over here, and it keeps on loading it up. And then over here, E, the maximum load is basically the maximum load it can take, or stress it can take, right? And it goes, and eventually then it just kind of breaks off. And that's the fracture point, or the load where it actually breaks. So this is a real life graph of an actual tensile test. So if you do any tensile test, it will roughly look like this. Some materials don't actually yield, but I don't want to get into that. So what's important to note here is basically these limits, right? So this is called the elastic limit over here till C. This is called the plastic limit. I'm not sure what your textbooks call it. Is there any questions, guys, based on this? You know, I'm saying a lot in a short space of time. Any questions, guys? We can make a discussion, guys. Don't feel tense. Camilla, Brandon, Eden. Is it Aiden?
We don't have any questions. I think we can continue.
Okay, thanks. Eden, okay, thanks. Aiden, okay. Yeah, so that's basically what happens with the actual tensile test, guys. And then yeah. So yeah, that's basically it over there. From the load extension graph, basically what we do is divide this by area and divide that by length, and we get the stress and strain, which we kind of talked about just earlier on. So yeah, we're just gonna, again, I don't know if you can see the slides. This is what what it basically looks like over here. I did do this lecture. I think it's on a YouTube channel, which I posted it, and maybe if you guys would like to watch it, you can always just watch it in your own time. But anyway, that's what's going on here. So anyway, let's start to solve that particular problem. Okay, I'm just gonna share my whiteboard again. Right. Okay, let me know when you can see it. You guys see it?
Can see it.
100%. Okay, guys, let's again same graph. The typical question which they give, I've seen on the N5 papers as well, is this over here, right? Okay, so the test is already conducted, right? And we get the values, and now we have to compute the relevant parts over here. Okay, so let's quickly try this. This is coming from the Wickens book, I believe, not the Toit book. That's where I got it from. Okay, let's see where we are. So the first part is they require the stress at the limit of proportionality, right? So you have to look at the graph, and over here, and they tell you here the load at proportionality 68 kilonewtons, which is over there. and giving you the extension, right? So that's the first thing. So again, my stress, if you recall, stress is, let me just do it properly here, 3.1. Stress is force over area, right? Okay. And so what happens is here, we now have to take the actual stress over here, which is, sorry, the force at the limit at proportionality, which is 68, and then divided by the actual area there, right? So the area, again, is a steel test piece of diameter 16 mil. So that's going to be pi over 4 times 0.016 squared, right? That's the first one. Colleagues, are we all on the same page here?
Yes.
Yeah, so basically pulling data from there, and we're just going to use the basic formulas over here. Okay, so can Anga maybe give me that stress? What is the stress there? Louis or Somila?
338.204.
Okay,
megapascals.
338.204.
That's what I'm getting.
Megapascals. Yeah, that's definitely correct. So yeah, so again, this limit of proportionality. So if we apply a load of 68 kilonewtons and release it, the steel sample will go back to its original state. Who would have thought that steel behaves like an elastic? But it's possible, right? So that's definitely the right answer there. Now the next thing, it's called the Young's modulus, and I didn't mention it in the previous one, right? So the Young's modulus, guys, you can only calculate within the limit of proportionality over here, right? It's this, they get E over here. Okay, so that's E. That's your elastic modulus. It's basically the gradient. Well, it's the gradient of that that line over there, right? So stress over strain. Okay. In this case, extension over load, but yeah, it's the same thing. So we require the stress value and the strain at that particular point, right? So I think we can use we can use any value until I actually told the yield, but it was not the yield, so we can use any value here, right? So I think, what did they say here? That's loaded fracture. So we have to use the same stress here, right? So guys, we need to now compute the strain, right? Because we already have the stress here. So what is the strain at the limit of proportionality? Remember, strain is going to be X changing length over L, right? So let's quickly get that strain. Can we get that strain, please? So the change in length was given there 130. Right? Colleagues, are we still here? Are we tired from work?
It's 2.653.
2.653, right? Is that all? I mean, okay. So what did you do here? You said 130 this divided by what? Is anyone aware of which length to use?
Is that the original length or the change in length, sir?
This is, the top is the change in length, the bottom is the original length, L. Which is essentially here, that's the gauge length over here.
The 70 millimeters.
Exactly, that's the actual length here. So we can have that as 70 times 10 to the power 3, -3, sorry, or 0.07, entirely up to you. And Chief, your answer, I'm not sure if I just missed you.
No, I made a mistake, sorry.
Okay. Yeah, guys, I don't know how you guys are going to do this, man. It's your...
I'm getting 1.857 millimeters.
That's correct, Agnes.
I get the same, yes.
Yeah, so that's the strain, right? Yeah. Okay, so once we have that, we can now basically put the stress in and put the strain in. So again, guys, the elastic modulus only works in the limit or proportionality. I hope that is clear to everyone. Eh? You cannot use any other values besides that. Okay, so we just put in 338.204 power 6, and we divide that by the 1.857 times 10 to the negative 3. Just give me 2 minutes quickly, a toilet break, and you can now just compute the elastic modulus for me.
One 182.124 gigapascals.
I get the same, yes.
Yes.
All right, guys, I'm back. What is my elastic modulus?
One 182.124 gigapascals.
182.24, no? GPa.
Yes, sir.
Yeah. This will tell us what type of material it is. I'm not sure what is 180 gigapascals. I need to have a look. Yeah. Do we all concur with this value?
Yes, I got the same.
Yes.
Okay. But I'm hearing a but. Okay. Right. Ooh. Can we move on?
Yes.
Sure. Okay. So now let's look at something called the yield stress, right? Very important factor. Again, the yield stress, right? If any stress more than the yield, it will start to permanently form. Anything less, it will retain its shape. So the yield will be typically given, it's 90 kilonewtons, and we have to use still the same area as before, right? So all we do is locate where the yield is. In this case, the yield is given as 90 kilonewtons over there, right? So that's force over area. That's 90 kilonewtons. And we divide it by that area we got in the start over here. There's a lot of contentious issues with area, but anyway, I don't want to get into that now. Okay, so it would be 90 divided by the pi over 4, 16 millimeters squared. Okay? What do we get there? Colleagues, are we all at home or?
I got.
Getting
It's fine. Go ahead.
447.
Go ahead, yes. How much? Louis or Anga, you were saying something?
447.623 megapascals.
447.
I get the same, yes.
Yes.
447.662.
23, yeah.
623.
Megapascals.
447.23.
623.
Oh, okay, got you. Okay, MPa. That's correct. Okay. All right. So again, the yield stress, right? Any stress more than that or any load more than 90 kilonewtons, the thing will start to permanently form. Now they want something called the breaking stress. I do want to make you aware the actual proper terminology for this is called the ultimate tensile stress. I don't know if you guys are familiar with that. Let me use a bit of color here. It's called the ultimate tensile stress, right? Or it's called the UTS. So when they're saying the breaking stress, that's what they actually mean right? Okay, so
I was keeping
yes.
the strength.
Sorry?
I was keeping 3.4.
Let's go 3.4. Oh, my bad. I meant 3.4. The tensile strength. Yeah. Sorry. They should have said the tensile strength, the ultimate tensile strength. So it's the same thing. So it's 3.4 actually. Yeah. Sorry about that. I'm not talking about breaking. I'm talking about that one. Sorry. Because breaking, so they're using different terminologies here, which is a bit of a problem. So the tensile strength is actually the ultimate tensile strength, which is the max over here. It's this part here. That's what that actually is. Okay. Sorry, man. So now let's so we need to use the maximum load. And again, right? We have to use the same area. Right? That's what I'm saying, it's very contentious with the area, but we have to use the same area, right? Let me quickly move it here. Let's go over here. 3.4 is stress equals force over area. And in that case, it's going to be 130 kilonewtons divided by that area again. Okay. Normally the software can do this for you, you know. So yeah, we typically get the values immediately. Okay, so we go what do you get there for that one? That's 3.4.
I got 664,567 what's it? Megapascal, sorry.
So it's 646.57.
I got I got 567, but 571.
No, that's fine. Yeah, that's fine. These are very real life values. I've seen this looks like a high carbon steel though. I'll be honest with you, especially with the 646 megapascals. That's the UTS. That's the maximum load. Now, apparently, let's look at 3.5. I'm sure everyone got that.
Yeah.
Yeah. So then, now we must be very particular now with the next two. So there's the breaking stress and the actual fractioning stress. So we don't typically look at these values, right? Unless we want to go into detail with the material. So normally the yield and the UTS is the main ones. On the macroscopic scale where we actually care about. But when we really want to check properly, we look at these particular ones now. So the next one is a breaking stress, right? That's 3.5. So the breaking stress, if we have a look now at our, what is this? At our thing over here, our breaking stress should be, it's a load at fracture, right? So this is what's yeah, okay. So we have to use where it breaks, right? This is where the specimen actually, you know what I mean? It breaks like it goes into two pieces. So, but now I'll tell you the difference right now. So 3.5 against a force of a simple stress force over area. But for the breaking stress, so to say, we have to use 70 kilonewtons, right? That's given over here, just to show you, divided by the original area, right? So still 16. So just be aware. I'm not sure what the other textbook says. So that's going to be 70 kilonewtons divided by the pi over 4. You must know what that is, okay? So that's the breaking stress, okay? So what do we get for that? I want to put 3.6 just here. That's the breaking stress, right? And that's on the actual area.
It's 348.151 megapascals.
Okay, 348. I got that. 151 megapascals. Great, right?
Correct. Yes.
Yeah. So that's the breaking stress. Now, we're now talking about why these contentious with the area, right? So the area mostly stays the same until the limit of proportionality, and after that, obviously the area decreases because the specimen is starting to break. It kind of necks, so to say. So when we want to compute the actual stress the specimen is under, right? And that's going to be based on the area just before it actually fractures. And you'll find that over here. Can you see diameter of the fracture? than 9.8. So for the actual fractional stress, you mustn't use 16 more. You have to use now the 9.8. Am I clear? I hope everyone is with me here. I want to perhaps show you. Yeah, I'll perhaps show you. So you have to use that next. Yeah, it's just difficult for me to rush through things without teaching, but okay. Yeah, it's just I'll show you what it looks like here. A picture speaks a million words, right? So this is exactly what's happening here. Specimen looks like that. We have a gauge length. We break the specimen, it looks like that. So what I'm saying is that, can you see now, once it's broken, there's a reduction in area from the original. I think we all can imagine this. I mean, so the area we're using now is that area. Am I clear?
Yes, sir.
Yeah, okay, cool. I'm not sure. Yeah, okay. So let's use it's the 70 kilonewtons again, all right? Divide that by 5/4 times 0.0098. Again, you can go 9.8 times 10 to negative 3. I believe it's 2 zeros there. Yeah. Okay. Right, and this should be a very, very high value at the point of breaking. So very, very high value.
So 928.017.
Okay, 928 times 0.17. Yeah, got it. Yeah.
Pascals.
MPa. Okay, megapascals. Okay. I've never seen a load this. Actually, I'm lying. I did see something reach a gigapascal worth of load. That was a massive diameter. But anyway. So again, right, the actual fractional stress is at the point of breaking, which is that particular thing. Right? Just making you aware. Okay, now we're going to end off after those two questions. Then I want us to have a small discussion. And then, then we're basically done. So I want to make you aware now. So there are two metrics over here. This is called the percentage elongation and the percentage reduction in area. What these are is a measure of ductility. Right? Is anyone familiar what ductility is before I move on? Ductility and brittle. Anyone familiar? Yes or no?
No.
No.
No, okay, no problems. Okay, so I just want to show you something quickly, right? Yeah, I'll try not to lecture too much next time. Hopefully you guys have went through the stuff. I hope you guys, I don't know what you guys mind and don't mind, but anyway, we always talk. So we have I'll show you some typical graphs quickly, right? Of stress and strain here, right? So see what it looks like. So you have different materials over here. Can you see that? And materials which looks typically around, see like that. This is what we call brittle, and that is what we call ductile. All right. What is the difference? So ductile basically is when we load the material, it kind of stretches, eventually breaks, right? And brittle is the converse. You load it up, and it just breaks immediately. Are we all on the same page there?
Yeah.
Yes. So that's the difference, right? So your typical carbon steel or mild steel, if you load it up, it's for stretch, and then break, right? So there's time to scream and the body collapses. But if you have like cast iron, for instance, right, and you load cast iron, it immediately reaches its maximum load and then it'll break immediately. It won't stop pull. You know what I mean? It doesn't behave like an elastic. It just breaks immediately. So ductility is the ability to kind of like, you have some time to scream, and ductility is like there's no time to scream. I mean, brittlity or being brittle, there's no time to scream. It's basically sudden fracture. I hope you all got that. Okay?
Yes.
I hope it was useful. So But the reason why I'm mentioning this to you is because these values over here, your percentage elongation reduction area, tells you how ductile something is or how brittle something is. So typically values over 20% is deemed ductile. Values less than 20% is deemed brittle. Yeah, I don't know. I don't think the textbook tells you that, but okay, cool. How do we compute these values? Your percentage elongation, I think we're 3.7 now, right? Yeah. According to the textbook, I also know write it out the way they're writing it. It's gonna be percent elongation is a change in length, right? Over your original length, right? Times 100. Okay, so that's percentage elongation. So then what we have to do is go back to our increase in that over there, right? Total extension, sorry. That's 26 more, right? Can you guys see that?
Yes.
We take the total extension of the whole story, which has happened, and then we just divide it by the gauge length of 70 more. That'll give us the percentage elongation. Okay, is it clear to everyone? So take the extension at fracture, the total extension, and divide it by, what's it? By 70. That one is, okay. So that's 26 divided by, let me just, so it's 26 divided by 70 times 100. Okay. Times it by 100, obviously it'll be in percent, so it'll be 37.142%. 143 maybe? Yeah. Did we all get this?
Yes.
Yes.
Yeah. So that tells you it's more than 20% that this is a very ductile material, right? It'll stretch before it breaks. The other metric we use, and this metric is used for also for tensile testing, but it's normally through thickness tests to ensure that because sometimes we load through the thickness of the plate. It's basically big D squared minus small d, also not big D. Just bear with me.
Yeah.
It's the diameter before it's the diameter before we conduct the test, right? The original diameter, and then minus the diameter of the fracture. So you remember that sketch I showed you? So initially we had how much was it again? 16 mil, and after it breaks, it becomes 9.8, right? So those two diameters. Are we on the same page? So we just go, yeah, we just put in the 16 squared minus, what is it? 9.8 squared divided by 16 squared. Okay, let's quickly get that one, and then we're basically done, and then we can have a chat. So 62.48, everyone, times 100, obviously. 484. Brandon, Lucy,
Yeah.
Annaliso, got it? Somila, got it?
Yes.
Okay. Okay. The rest of the colleagues, do we all get it? Eden, Aiden, Louis,
Yes.
you got it?
Is I got it?
Yes,
Okay, great,
got it.
great. Okay, okay. So guys, I think I'm gonna end it here because it's a lot of things, a lot of concepts which is at play, right? I want to make a proposal. Obviously, I want you guys to review the session now, but I just so how are we going to conduct the sessions? I mean, the best way, in my opinion, is that you have to go through the things before. Right. What I recommend is do the examples, do exercises, and then once you've done the exercises, go to the past papers immediately. I would do that, right? Examples, exercises, past papers, so you can exactly see what you're going to be asked, right? I'll put up a site where you can get past papers or an app, so you can exactly see what kind of question they will ask, right? The second thing is, I'm hoping that you guys cover the material and then maybe find certain problems I must go over, then I can go over the challenging ones. Am I clear, everyone? Are we on the same page?
Yes.
Yes, so yes, cool. Thanks. Yeah, I mean, I'd love to teach you guys, but if you like me to teach you stuff, I don't mind spending like a good 20 minutes just going over concepts before we solve problems, right? But I'm not sure if you guys like that or not. So I don't know. What I can say for the next chapter, we are doing module 2 next, but please make sure you understand the compound bars, because compound bars feeds into module 2 and module 3. Am I clear, everyone?
Yes.
So make sure you spend a lot of time understanding the compound bars part. It is of utmost importance. Like it's a concept which you're gonna need like in the next 2 modules. And if you don't know it, then everything else becomes a bit of a stretch, man. Let me just confirm that. Yeah, bars in series and parallel. That's what you must know. For both two. Okay, so guys, I want some feedback from you guys. Are you guys happy with us solving problems like this? Is there anything, how can I support you guys further in terms of your preparation? I'm opening the door here, opening the house. Please talk, guys.
Yeah, on my side, you can teach before we tackle the questions.
Thank you, brother. Okay. Busi, you want to say something?
I agree as well.
Yeah, okay. Louis, Anga, Brandon?
I totally agree with that.
Okay, yes. Anga, you're saying something? Thanks, Brandon.
Yes, I was gonna say also I agree with
Yeah.
that. And I wanted to ask
yes.
I'm not sure if we're supposed to have classes from 6 till what time? Is it till 8 or?
Yeah, yes, it's supposed to be, man, you know. It's not like fully. I just thought I think I didn't want to cover the compound section if you guys didn't go over it. You understand?
Yeah.
So I want to give you guys a time to. It's our first session, because I can do it, and then like people's like, "Hey, I'm not there yet," and then it kind of goes over your head. I don't even make sense.
Yes, no.
Yeah, so I'm just giving. So we have a procedure of what we're gonna do, because next time I come, for sure we're gonna do compound, because I need to spend some time there. That is my plan. Yeah, so I just thought we get the feet wet first, so you can see how I teach. If you're happy with it, you know, how can I support you guys? And then yeah, but it's 6 o'clock's a good time, and then yeah. But I mean, what you can do now, you can do some problems, and I'll be available till 8. You know what I'm saying to you? I'll be on WhatsApp with you guys, to assist you anyway. And then next week we can start full force. I don't know, how prepared are you guys? Are you guys keeping up, or you guys are behind? I'm not sure. Please tell me now. Angus, Eden, Busi, Louis?
We have to. I'm saying we don't have a choice.
It's a short semester.
I'm a little bit unsure what's happening now, sir, but I work nights, sir, and I'm at work currently now, so.
Yeah, you see what I'm saying? That's what I'm saying, man. Because I mean, I can talk and solve stuff, but if you're behind, it's not gonna work, man. But by next week, guys, we know the procedure, right? Go over compound bars, go over module 2, and I'll put up some problems, and then we can go over it. Eden, do you want to say something, brother?
Yes, is class going to be like every Tuesday and Thursday, or every day, or it's going to be?
No, it's just Thursday. Just 6 to 8, man. Yeah. Unfortunately, I still have other work to do. You know, I'm employed like full time. This is like my side work, if I could say.
Okay.
Yeah, so 6 to 8 next time. For sure, we're gonna finish the time. But like I said, guys, if you want to do some problems now, you can consult me on WhatsApp till 8.
Yeah.
But yes, Sumila, you're
So
saying something?
you spoke about YouTube channel earlier. If is there any videos that are there, you can share a link with us, please, man, so that we can push our
100%. Yeah. Okay, no problems, guys. Like, but next week, please be ready, man. We're gonna be pushing nicely. You know what I'm saying to you? You know, I'm just giving this breathing space now. But immediately go tackle the exercises, man. Don't even waste time. Don't even waste time. Just get your feet wet. So yeah, guys. So again, what I'd like, go into the book, do problems. If you're finding ones that you're struggling with, tell me before the time. I can prepare them, then I can solve them during our sessions. Alternatively, I will choose problems and then we can go over them. Is that okay?
Yes.
Okay, thank you. Okay, thank you, colleagues.
Sir,
yes, Brandon, go for it.
Yeah, I just want to know, under what book are you working at?
So I posted that already on the group. I don't know if you've got that already. It's the
Okay, yeah, I got it.
Yeah.
I got it, yeah. So is it at the weekends one or what?
No, it's the Toit one I'm working from. That's the one I received from. Yeah.
The blue one. Okay.
No, not the blue one. It's like white book. Yes. But I believe.
Oh, yeah.
Yes. I believe they have the same content. I'm not seeing the updated version of the blue one. So as long as it's the new curriculum, yeah.
Okay. Thanks.
Cool. So again, guys, I'm hoping to have enough sessions with you. I might not be able to have sessions with you all the time, but at least I'll have, at least most of the lessons I have sessions. So I'll be sending questions. You'll solve them, and I'll give you the answers. You can see if you're fine. So I'll try to have a session.
Sorry, I've got a question.
Yes, bro. Go for it.
Can we message you during the week sometime, like on a Wednesday, Monday? If we're struggling with something, maybe 4-6 side.
Yeah, so what I prefer is that, like obviously we're busy, right? So like 6, our session time is from 6 to 8, right? So on a Thursday, right? So I think as much as I'll extend, guys, like maybe on a Wednesday afternoon, on Wednesday evening, ask me questions then, and then on a Thursday only. Life, family, studying, what. So I'm available that time, right? So on a Wednesday, you can ask me questions, and on a Thursday. Are you with me, Angus?
Totally fine, sir. Yes, I understand. Totally fine, sir.
Yeah. So just do quick consulting, and you can engage in the group, right? So, but like I said, sometimes I'll send you questions, you solve them. I'll try to have as much online sessions as possible. It's not like it's compulsory for me to do that, but I like the engagement that we have, and I really want you guys to work hard so I can support you properly, man. You know what I'm saying to you? Yeah. Okay, colleagues. Next 30 minutes, try to do a question in the thing. If there's any problems, let me know. Again, it's on correspondence. You're supposed to be the master of your own studying. I'm only giving advice. So let me know, man. But thank you for attending, guys. And by next week, again, compound bars of module 1, and then also start on module 2. Is it clear, everyone? Just mute that.
Yes, sir.
100%. I'm just muting the people. Yeah. So just please, right? So again, do compound bars in module 1 and then start on module 2. And then if you have some questions there, I'll solve them. If not, I'll bring questions and we can solve them. Okay. All the best, guys. I'll see you next week, same time, same place. Cheers, guys.
Thank you.
Cheers.
Bye.
Thanks, Manuel. So appreciate it. Thanks, Louis. Thanks.